The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and welcome to the Great Lakes Seminar Series, co-hosted by the Cooperative Institute for Great Lakes Research and the NOAA Great Lakes Environmental Research Laboratory. It's my pleasure to introduce today's speaker, Dr. Jay Martin from The Ohio State University. Jay is a professor of ecological engineering who analyzes and integrates human and natural systems. As a faculty member in the Department of Food, Agricultural, and Biological Engineering, and a faculty co-lead for the OSU Sustainability Institute, he seeks to use natural systems to improve water quality and increase sustainability. His interdisciplinary research links field studies, watershed models, and socioeconomic analyses with stakeholder groups to investigate connections between downstream water quality and management practices in upstream watersheds. Before I turn it over to Jay, I'd like to remind everybody to please leave their microphones muted for the duration of the webinar. At any time during the presentation, you're welcome to enter questions into the chat box, and I will read those to Jay to answer at the end of his presentation. With that, I will turn it over to Dr. Jay Martin. Welcome, Jay.
Thank you, Mary, and thanks to everybody at Siegler and Glurl for the invitation to present today. I appreciate that, and welcome to everybody online. Sorry that y'all can't see me. We tried to make that happen earlier, but there's some kind of snafu between the GoToWebinar and my operating system on my Mac that won't let that happen. So we'll just have to do it by voice and slides today. So today I'd like to talk about a public-private partnership that we developed with the agricultural community in Ohio that allowed us to identify and manage elevated phosphorus fields. Now, this is really important because these fields likely emit some of the greatest amount of phosphorus per area within the Western Lake Erie Basin. So if we can identify them and get management to these fields, it's likely that we can make a pretty big dent in the phosphorus reaching Lake Erie. So after presenting how we formed this partnership and some preliminary results, I'd like to close by our efforts to expand this approach to reduce nutrient runoff so that we can reduce harmful algal blooms across the Western Lake Erie Basin and perhaps other places as well. So what I'm going to do, a little unusual beginning, is I'm going to start with a video here. This is a 2-minute video. It does a great job of summarizing the project is one reason I'm going to start with it. Another reason is because if any of you have not voted today, you could watch this 2-minute video and then you could go vote, which is going to be more important than anything I have to say today. So with that, I'm going to go ahead and start this video, and then I'll jump back on in about 2 minutes.
A toxic algae bloom. Individually, algae are microscopic and insignificant, but in large numbers, they can be harmful. In the Western Lake Erie Basin, they can become large enough to close our beaches and cause drinking water bans. Algae growth is driven by phosphorus. Phosphorus comes from all kinds of sources, like cities, neighborhoods, and farmlands, and a lot of progress has been made to keep it out of the water. But we're finding some farms have elevated levels of phosphorus in their soil because of soil type, geography, or historic land use. And high levels of phosphorus can lead these elevated phosphorus farms and travel downstream to grow algae. So if we're to really protect the water in Western Lake Erie, we need to look at elevated phosphorus fields. A partnership between researchers, nonprofit groups, government, and businesses are working together in a large-scale partnership. The goal is to identify elevated phosphorus fields, help implement management practices, and study their viability and effectiveness. The information and experience gained can be used to scale efforts to the entire Western Lake Erie watershed and beyond. Each farm is different, and we work with each farmer to figure out which practices work best for their land. So the goal is to slow water exiting the fields with practices like phosphorus filter beds and wetlands that hold water and treat phosphorus before it goes downstream. But these practices can be expensive to install. So the partnership helps the farmer install the practices and will monitor the effectiveness at keeping phosphorus out of the water. Our Great Lakes give us water to drink, places in which to play, and countless economic opportunities. This project is focused on keeping our waters clean and our farms productive, now and into the future. A toxic algae bloom. Individually, algae.
Okay, so that was a really good intro to the project. I want to thank the Nature Conservancy and Bigfoot Media, who collaborated to develop that really nice introductory video that we've used many times to introduce this project. And you can, if you want to see that video again, there's two websites down the bottom of the screen. You can visit either of those and see the video. The one on the right-hand side is the 4R certified site in Ohio, and they're also partners in this project as well. Okay, with that, I want to move on and quickly point out that while we're focused on the Western Lake Erie Basin here, that these harmful algal blooms are really a national problem. There are several sites in the Great Lakes. There's actually hundreds of sites internationally. So the hope is that what we learn here in the Western Lake Erie Basin about managing elevated phosphorus fields can be used elsewhere, because these elevated fields don't just exist around Lake Erie, they exist throughout the world. So with that, I want to give a little bit of background about phosphorus in Lake Erie and some of the rationale for this project. So I think many of us know that phosphorus is the major cause of harmful algal blooms in Lake Erie. It controls the size and extent of these events. Nitrogen plays a role in the toxicity. And most of the phosphorus that comes into Lake Erie is coming from the Western Basin as opposed to coming from the Detroit River. And when we divide that Western Basin up even more, by far the largest amount of that comes from the Maumee River. So if we want to be able to reduce phosphorus going into Lake Erie, it's good to focus on the Maumee River watershed. And our group's done a lot of work there over the years, and that's where this project is focused as well. In the bottom right are some other pieces from the Great Lakes Water Quality Agreement. So we're focused on spring loads mostly to affect harmful algal blooms. We're really focused on the dissolved reactive phosphorus because that's what's most available of these blooms. And back in 2008, there was a commitment, you might say, to reduce these loads by 40%. And the goal is to meet those reductions 9 out of 10 years, knowing that some years there could be a very large rainfall year, and that would be very hard to meet the target then. So again, we're focused on the Maumee River, trying to reduce phosphorus. And our group has done a lot of watershed modeling in the Maumee River watershed. And this slide's a little busy, but I want to point out a couple things here that really guided this project and the focus on elevated phosphorus fields. To orient you to this slide a little bit, over on the left-hand side, you see baseline labeled, and that's the amount of total phosphorus and dissolved reactive phosphorus. On average, it's coming out of the Maumee River, that came out of the Maumee River between 2008 and 2018. The other bars you see to the right of that are results of our watershed model analyzing different potential management scenarios. What we're trying to do is get to that green area on the top. If we get to that green bar on top, that means that we've met the target 9 out of 10 years. And you see most of these bars are above the baseline, so we're making progress, but we're not reaching that green area. The one thing I want to point out that's especially relevant to this project is comparing random application of management to target application of management. So these two scenarios you see here, both for TP and DRP, they're identical, except in the scenario to the right, we targeted the application of those plans to areas that were losing the most amount of phosphorus or had the most amount of phosphorus runoff. And you can see by doing that, we greatly increase the number of years we met the target. So there's a tremendous advantage if we can locate these practices to where they're most needed. And there have been a lot of other important results from the watershed modeling, but that's really what guided this project that I'm talking about today. So we know that these spots are out there. The question is, where do we expect to find these DRP hotspots, if you will? or spots that disproportionately lose phosphorus, larger amounts of phosphorus. Luckily, there's been some previous work done that has looked at the relationship between soil test phosphorus, and I'm going to use this term a lot, so that simply means the amount of phosphorus that's in the soil, and how that relates to DRP concentrations of runoff. And as you can see in the graph here, the higher concentrations of soil test phosphorus you have, or the more phosphorus you have in the soil, the greater probability there is for higher amounts of dissolved phosphorus to run off that field. Okay, and this has been proven across the country. One of the spots was in the UK, and then Kevin King, there's a reference on the bottom there, has also demonstrated this within the Western Lake Erie Basin, and these are strong relationships. So this tells us that if we can find agricultural fields or other types of fields that have high soil test phosphorus, these are probably some of the hot spots that we're looking for where we'd like to locate management. And lastly, the best management practices should be more effective at these sites, like I showed you with the results from the watershed modeling. So we also know that these sites exist in the Western Lake Erie Basin, and we know that because of the soil results from soil tests that farmers submit to soil test labs. So this is data from soil testing laboratories, and there's a couple citations in the bottom here so you can find it yourself. And you can see that some counties in Ohio, maybe 10 to 15% of those samples are coming back above 100 milligrams per kilogram. Some of them only 0 to 5 are, but we know that these sites are out there. The other thing we needed to do for our project was we had to draw a line in the sand and determine what we were going to classify as elevated phosphorus fields. We decided to draw that line in the sand at 100 milligrams per kilogram. Why did we decide to do that? There's two pretty good reasons for that, I guess. One is that it's 2.5 times greater than the agronomic recommendations. So the agronomic recommendations for corn and soybeans is 40 milligrams per kilogram phosphorus. So this is 2.5 times that. The other reason we chose 100 is because it's a nice round number, to be honest with you, but mostly because it's 2.5 times greater than the recommended agronomic rate that's needed to grow, to have productive yields of corn and soybeans. So in summary, we know these fields are out there, and this isn't something that's new. Many people have agreed on this for quite a while, but the problem has been it's been very hard to locate these fields and get management to them and determine how much phosphorus is coming off these fields, and also how effective can management practices be on these fields. So that's been a real barrier that we were able to surpass with this project. And the way we were able to do that was by forming a public-private partnership with the agricultural community. So the thing we knew going into this is by working with crop consultants and nutrient service providers and other projects, we knew that they had a lot of the data, that they knew the soil test phosphorus concentrations on many fields. We also knew that they were trusted entities with farmers. So many farmers have been working with nutrient service providers for a decade or maybe even 2 decades. So they have very long-standing trusted relationships. So by forming a research team with the Nature Conservancy, we first reached out to the Ohio Agribusiness Association. The Ohio Agribusiness Association is very important because they organize the 4R certified program in Ohio, which tries to get the right practices to the right field. And they also have many nutrient service providers or crop consultants that are 4R certified. So the Ohio Agribusiness Association reached out to 4 possible nutrient service providers and asked them if they'd be interested in working on this project. They said they would. So then we got in touch with them and explained what we were trying to do and how we'd like to work with them. And they said that indeed they would like to work with us that way. And they made a link with the farmers. So they could identify farmers who had the type of fields we were looking for. And then they could reach out to the farmers to see if they were interested and wanted to talk to us further. And then if they would, we could start to talk to those farmers and look at their fields. And if things worked out all right, we could actually monitor their runoff and install management practices. One of the things that helped this project is that it was a 5-year, $5 million project from USDA, so we could use those resources to pay for the practices that we installed on these farms. So there was no cost for the practice to the farmers, and that definitely eased the installation of these management practices for sure. So today what I'd like to do is step through the project objectives. And I'll talk about those briefly here, and then we'll get into them in more depth in just a second. So objective 1 was to, first of all, locate these fields and install and monitor best management practices, or what we refer to as BMPs. So we're trying to have 14 total fields. USDA and Kevin King's group is another partner on this project. So they already had 2 fields with elevated phosphorus concentrations, so we could include those in the network. And we have identified 12 new field sites from the public-private partnership. And the questions we're looking at there are, first of all, do these fields disproportionately contribute to phosphorus loads? The assumption is that if you have a high soil test phosphorus value, you're going to have high runoff. Is that always true? Is it usually true? And then how effective are best management practices? So which best management practices are most effective at reducing those high rates of phosphorus runoff? And then objective 2 is our attempt to expand the reach of this project. So we're using socioeconomic analysis to try to determine what are some of the barriers to adopting these practices. What are some of the barriers to having nutrient service providers participate in projects like this? Is it simply economic, or are there other things that are involved? If we can demonstrate that it works on these 12 fields, we'd like to be able to replicate this approach throughout the Western Lake Erie Basin so that we could address other elevated phosphorus fields. The watershed modeling, we'd like to try to answer the question of, if we can focus on more elevated phosphorus fields, how much of a dent can we make in the phosphorus reaching Lake Erie? So if we could identify 50% of the elevated phosphorus fields in the Western Lake Erie Basin, get management to them, how much can we reduce phosphorus by coming into Lake Erie? And then objective 3 is our outreach and engagement. And there it's all about trying to take some of the learning modules we're developing and bring more focus, bring more awareness to legacy phosphorus fields or elevated phosphorus fields, and what type of management is appropriate for those fields. We'll talk a little bit about that in a few minutes also. So some initial results, we were able to look at a lot of different fields. So this is about 22,000 soil samples from over 3,700 fields. And what you can see here is that earlier I said that about 5% of the fields, if we look, or 5% of the soil analyses come back above 100. We found something pretty similar to that here. We found a little bit above 6% of the soil samples on these fields come back above 100. Some of the encouraging news, I guess, is that by far the majority of the fields are well below the agronomic, or are below the agronomic rates. Only 36% are above the agronomic rates. That means that got to do some math here, but 64% almost are below that agronomic rate. So just looking at some distributions here of soil test phosphorus and some of the initial fields we looked at. And then something else we found out, these are 2 fields that we looked at in our study. And the top field is really typical of what we saw across the fields we looked at. And so you see that there's a lot of green area in the top and bottom of that field. And as you see in that scale to your right, those areas are below 100, so they're not what we classify as elevated phosphorus fields. That blue or gray area in the middle is just above 100. And so that's really typical. So instead of having a whole field that's elevated, it's usually just a zone in that field. So that makes things a little bit more tricky going forward, is that it's not just locating an elevated phosphorus field, but it's really locating an elevated phosphorus zone within that field and trying to get management to the water running off that zone. On the bottom of that middle panel there is something that we did find a couple times, but was very rare. You see that field there, it's all close to 200 milligram per kilogram. And in that case, that whole field is what we will call in the elevated status. But again, what was more typical is that field to the top on this panel here. So looking across some of these fields, we requested spatial information on about 46 fields from interested farmers. The next thing we had to do as we worked down to identifying actual field sites is we had to determine would this field work for our study. So there are a number of things we had to look at there. Probably the most important of those was how the water ran off that field, and was that field hydrologically isolated. So by hydrologically isolated, you can see that there's a black line I drew around this field. That means that no water is flowing into that field from outside, from a neighboring field. So that means it's hydrologically isolated. So everything that we catch to the eastern side of that field there is coming off of that field. So that's pretty tricky. It's pretty hard to find fields like that. And then ideally, there's just one drainage point from that field so that we can put in one monitoring location. So those are some of the things we looked at. We also had to look at, is there enough room to monitor? Is there enough room for a management practice to go on the edge of this field? Is that possible? So there are quite a few things that narrowed things down pretty quickly, in addition to finding farmers that were willing to work with us and interested in the project. We also had to look at, so we had surface and subsurface drainage from these fields. So we had to be able to capture both of those to quantify the total amount of phosphorus coming off the field. Once we did identify some fields, then we had to think about what types of best management practices would make sense on a field. And there were three, excuse me, I have a drink here. There were three edge of field practices that we thought made sense here. One of those was phosphorus filters. One of those was constructed wetlands, and the third one was drainage water management. And we'll go into more depth about those three in just a second here. We are also considering in-field practices, and some of those are on the bottom of this slide. We haven't actually implemented any of those yet, but we could in the future. There's a few sites we're still monitoring and still evaluating what type of management practice we might use there. And this was guided by the BMP handbook that was developed by OSU Extension. There actually is a handbook. I think most people access the online version of this, which you can find. And then the ultimate goal here was to find the right solutions for the right field. So this was a collaborative effort for sure, with OSU Extension agents, with the farmers themselves, with nutrient service providers, and the researchers to identify what type of practice or practices made sense that would have the best chance of reducing phosphorus, what type of practice the farmer felt most comfortable with, what type of practice there was actually space for and room for. So there were a lot of things to consider in choosing a best management practice for these fields and for all fields. So when we look across our 12 or 14 sites here, this is the breakdown right now of the different practices we're using. I know it's a little bit confusing between 12 and 14 sites. So there's 12 sites that we've identified from this project, and there's 2 sites that are shared from the USDA. So we have a total of 14 sites. Of the 12 sites, 3 of those are phosphorus filters, 2 of those are drainage water management systems, 2 of those are or will be wetlands. And then at 5 of those sites, we are only monitoring right now. And I'm going to talk a little bit about that in the future, why we're just monitoring those sites. And you can see that most of these have been installed. There's one wetland, which we're building right now. I'll show some pictures of that in a second. But we're very close to, we've identified the 12 sites, and we're very close to getting monitoring and management practices at these sites. To be honest, it's just difficult, and it takes a while to identify sites and work with the whole group who's going to pick a site and pick a management practice and then work with a contractor and get that in. So I feel like we're doing really well after 2 years to have the bulk of these sites installed and being monitored. Related to monitoring, as I mentioned before, we're fortunate to be collaborating with Kevin King and his USDA ARS group on this project. And we have largely mimicked or borrowed their edge of field sampling protocol for this project. And you can see a couple of those pictures here. The things we're monitoring for are, in addition to the flow, the amount of water, we're looking at total phosphorus and dissolved reactive phosphorus, nitrate, total nitrogen. And then the way we're doing that, if it's an edge of field practice, like a phosphorus filter or a wetland, there we can do the inflow and the outflow. So the inflow to our management practice tells us what's coming off the field and what's going into that phosphorus filter. The outflow tells us what's coming out of that. So by comparing those two differences, we can see how much phosphorus we reduced. And then an in-field practice, so drainage water management is an example of an in-field practice. There we use a 2-by-2 year approach. So we've actually put in these drainage water management structures right now, but we're letting the water freely flow out of them for 2 years, monitoring what comes off that field with no management for 2 years. And then we will activate them for 2 years, and we'll be able to compare what happened in the first 2 years versus the second 2 years to try to get an idea of how effective that practice is at reducing phosphorus. Ideally, we'd like to have probably a 4 and 4 year project, 4 and 4 years to compare. But in a 4-year project, we were limited to doing 2 years pre and 2 years post management. So here is one of our drainage water management sites that we've installed right here. One of the things that's important about drainage water management, it has shown some potential, but it also has some uncertain effects. Kevin King has looked at this and pointed out that there may be some concern about actually increasing phosphorus loading. So what could be happening here is while we're backing up the water in the tiles and holding that phosphorus back, there could be more surface runoff coming off that field and more phosphorus leaving from the surface. So it's really important that we get more of these drainage water management systems installed and monitored so we can try to answer those unknowns about how they work generally, and especially how they work on legacy phosphorus fields. Some initial results from our 2 drainage water management sites. We have 2 fields here, CC and DS. I will mention that one of the important parts about this project is protecting the confidentiality the farmers are working with. So we use field codes here. I have flashed up some of the fields so you can see some of the STP concentrations in the yellow, so you get a sense for the type of fields we're working with here. So I want to orient you to the graphs that I'm going to show some preliminary results from for these sites. So on the bottom of these graphs, you're always going to see a dashed horizontal line, and that shows the target goal of 0.05 milligrams per liter dissolved reactive phosphorus that we need to meet the goals for the Lake Erie Water Quality Agreement. Okay, so that's our goal, that dashed line at the bottom. So you can see that field CC, we have concentrations coming out of that field right now that are well above that, between 0.25 and 0.5. Our site DS, the drainage water, that's the middle bar there. That's also a bit above the 0.05. And then the surface water, we have much less samples, but you see that's a 0.28, so that's well above that limit. So that's one of the questions we're trying to answer here with drainage water management. Is it possible that there's higher concentrations coming off the surface, and if we put in the drainage water management and get more of that surface runoff, we might be encouraging more phosphorus runoff from those sites than we're stopping. So that's some preliminary results from drainage water management. Another edge of field practice we're using is phosphorus filters. And these are some designs that are well suited to elevated phosphorus fields because these function really well when you have higher DRP concentrations. And fortunately, we're collaborating with Dr. Chad Penn from USDA ARS. He's in West Lafayette, Indiana. We worked with him a lot, and he actually has some software called P-Trap. So if anybody's interested in phosphorus filters, I encourage you to look that up and check out that software. To give you an idea of the concentrations that we're looking for here, Chad has an ideal concentration of 0.2 parts per million. Again, 0.05 is the goal, and NRCS has an interim goal that's even higher than that, so 0.5. So these can work well when you have high amounts of phosphorus coming off these fields. They can also have a relatively small footprint. So as opposed to a wetland, these can be buried in a buffer, and that's what we're doing right now for the applications in this project. And there's also potential for these to be rechargeable over time. So there's media. You see the big block in the middle, that's a structure, oftentimes a concrete structure. It could also be a hole dug in the soil, and within that hole we put our media that can absorb phosphorus. So the way these work, you can see the structure here. We have a drainage water management structure that guides water into it. We have access to the top. So here comes our phosphorus going into the media. Water's flowing through, the phosphorus gets trapped in the media, and then clean water comes out of that system. I'll show that one more time here. So here comes the phosphorus. It's like a video game getting trapped in the media, and clean water comes out of the system there. Most of what you see there are access ports so that we can monitor the water coming in and coming out of the system. Those manholes on the top allow us to get access to the media if we want. So if we need to, we could actually use a vac truck to remove the media. But they also let us be able to monitor it and see if it's clogged and things like that. One of the important aspects of these phosphorus filters is that they're relatively expensive. Okay, they're much more than a buffer strip or a drainage water management. You're actually, putting in a large structure in the ground and putting media inside that. There's a good bit of plumbing and engineering, as you see here. The largest amount of the cost often is the media, and we're using two different types of media here. One is called Alcan. That's an engineered media that's on the top chart here, top graph. And what's interesting about it is it costs, it's very expensive. So for 1.6 tons of that media, it cost almost $5,000. On the bottom table, in another phosphorus filter, we're using metal shavings that are mixed with sand or gravel. And so when we look at that material total, there we get 18 tons or almost 19 tons, and it costs us $1,500. Okay, now there's a trade-off in that the Alcan is more efficient. So with the Alcan, we need a bed width and a bed length of about 6 feet, 5 or 6 feet, and a media depth of only 1.5 feet. For the metal shavings, we need a lot more to do the same type of job. So we need a bed width that's about 11 feet by 12 feet and a media depth that's 3 feet deep. So the questions are, which one of these is more effective over time? We know which one costs more. It also depends on how much space you have within that buffer. If you have a big buffer, maybe you could use metal shavings to capture that tile outflow. If you have a small buffer or smaller footprint than you can use, maybe then you have to use the Alcan. So these are some of the things that we're trying to look into with phosphorus filters. It's a relatively new technology, especially being used next to agricultural fields. So we're trying to learn as much as we can about these in a pretty short amount of time so we can find out what are the best designs, what's the best media, and how can they best be used to eliminate phosphorus runoff from fields. Clogging has been a problem with past use of these systems. We're trying to address some of that with some novel designs on this project. So we hopefully won't have clogging, knock on wood. And this just shows you how effective these phosphorus filters can be. So we have two sites here. LH, you can see again, to orient you, that dashed line there, that's our goal for the Western Lake Erie Basin. So LH, you'll see that the concentrations there are over 0.5. And then the outflow is LH2. So the outflow is 0.02. So we have inflow that's pretty high and outflow that's 0.02 below that threshold that we're trying to meet. In field WE, which is on the right side of this graph, WE1 is the inflow to our phosphorus filter, WE2 is the outflow. So there are inflow and outflows 0.09 and 0.02. So just as we would expect, these phosphorus filters are really effective. They're especially effective now because we've just put them in. This is data from the first year. As the sites within that media become saturated with phosphorus, we would expect that the efficiency might go down and our outflow concentrations might creep up a little bit. That's another thing we have to monitor about these designs as well. But right now they're working very well. No clogging, and we're getting really good phosphorus reductions here. A couple other sites, we are going to be constructing wetlands. And you can see those sites here. One of them, we have surface flow coming off. The one on the right-hand side, we have mostly tile flow that's going to go into that. Actually, it's tile flow and surface flow that's going into that wetland. And this is really exciting right now because I have October 2020. And these are some pictures from yesterday and actually a picture from today. So we just barely missed getting this built in October, but I think it will be built and fully monitored by the end of November. So you can see on the right-hand side, we're actually creating the bowl that will be the wetland. On the left-hand side, you can see some of the field in the distant part of the picture that's contributing runoff to the site. So it's exciting to get one of these wetlands constructed and monitored and be able to see how well it's performing to reduce phosphorus runoff from these elevated phosphorus fields. And then I mentioned earlier on that there's a few sites where we are only monitoring right now. And the reason for that is because while some of these sites have relatively high soil test phosphorus values, we're just not seeing the runoff concentrations that we thought we would that really mandate management. So for instance, if you look at the CB field, if you look at that graph in the upper left-hand corner, the runoff from CB1 and CB2, all those are below the threshold that we're looking for. So it might not be necessary to install management at that site, despite having pretty high STP concentrations. You can see in that field map, some of those concentrations are north of 500 milligrams per kilogram. And then if you look to the right-hand side, the fields JS and FA, you see relatively or higher concentrations of phosphorus. So those locations, we probably do need some type of management to be put in those fields. So our plan is to use these results to guide our management actions. We're going to revisit that at the end of this year to see what we want to install, or if we want to install practices next year. And this is really interesting research, because definitely our hypothesis is that, you know, these fields with these high concentrations are going to emit large amounts of phosphorus or have large amounts of phosphorus runoff. But we're surprised by some of these sites that don't have that. And so it's be really important if we can find out what are the characteristics of these fields that make them unique, that allow them to have high concentrations, high soil test phosphorus values, but low amounts of phosphorus runoff. There could be things to learn here that we could apply to other legacy phosphorus fields. It can also help us guide our management. So at this, like the field CB, we could be wasting our time by putting management at this field, where other fields like FA or JS, it might make sense to manage that field. So what are some characteristics of these fields that lead these fields with high soil test phosphorus values to emit high or low phosphorus runoff? That's something we're trying to determine with this project. So our next steps for objective 1, we want to complete the installation of practices and monitoring. So we're working on our wetlands. We have one more phosphorus filter to install and one more monitoring to get in place. And then the next thing will be to look at, calculate load and loading rates. What I've showed you so far are concentrations. So we've been taking water samples from these systems and analyzing the concentrations in the lab. But what we really need to do is go combine the flows and the concentrations to get some loading rates. and look at the drainage area and look at loading rate per area and some things like that to really learn what's happening at these sites. And that's what we're going to start doing this winter. Objective 2, as I mentioned before, is focused on the socioeconomic analysis and watershed modeling. I'll start first at the bottom here with the socioeconomic analysis. So here we want to look at how can we increase farmer and NSP participation. So we do have a network here of 12 fields, and we have been able to identify farmers that want to work with us. But how can we expand this approach so that other fields that have elevated phosphorus concentration can be identified and can be managed? And how can we raise awareness of this issue and improve the management of these fields? So that's what we're looking at with the socioeconomic analysis. With the watershed modeling, right now, when we start our watershed models, we start with a homogeneous map of initial soil test phosphorus across the whole Maumee watershed. So using some of those results I showed you earlier, we'd like to have more realistic maps where we can have a distributed soil test phosphorus values within different zones within that watershed map, if you will. And then we can start to ask that question like I asked before: how effective will we be if we can get management to a quarter, a half, 3/4 of these legacy phosphorus fields? How effective will that be in reducing phosphorus being discharged into Lake Erie? Those are the questions that we want to answer with the watershed modeling portion of this project. We have made some initial strides with the socioeconomic approach. So we have interviewed only 4 farmers so far to try to gain some information about what makes them more or less interested in projects like this. The bottom line is it's not too surprising, but it's money, time, and effort that really guides their decisions is what we're looking at right now. And I do just want to give a big thanks to our nutrient service providers who are working with us. It's Nutrient Ag Solutions, Farmers Elevator, and Nestor Ag. Been amazing partners, and really this project would not exist without them, or OABA, Nature Conservancy, or USDA. So we have a great group working together. On the left-hand side, you get an idea of how many fields or how many farmers we're trying to reach out to in these different counties in Ohio to try to ask these questions to get more information about what are the barriers to being involved in a project like this and how can we overcome those. Another thing we want to do is develop learning modules. So we want to be able to increase the awareness of these legacy phosphorus fields or elevated phosphorus fields, and by that improve the management of these fields. And so one way we're doing that is developing a learning module here, and that's really being led by Greg Labarge and Jessica D'Ambrosio at OSU Extension and Nature Conservancy respectively. Also Stephanie Singer at Nature Conservancy is playing a big role in this. We have developed this, and we're going to start delivering this to NSPs and in other locations next year. Stakeholder engagement and outside evaluation are also really important portions of this project. So we do have a stakeholder group that we meet with twice a year, and we have representatives from these organizations that you see on the screen here. And then we're also working with the Center on Education and Training for Employment at Ohio State University to annually evaluate the project and see how well we're doing compared to our objectives. And you can see from this quote here, they think we're doing an okay job so far. Lastly, extension and outreach is vital for this project. So, we can find out what practices work best at these fields. We can identify these fields and find out how much phosphorus is being emitted from them. But if we don't engage other people with that information and have people use these management practices on these elevated phosphorus fields, it won't make a difference. So it's really important that we reach out on social media. I showed you the video we had earlier. That's one of the things we have on social media. We've been to several field days, presentations, and the learning module I just showed you before. We're going to use that at many different opportunities, including courses at Ohio State as well. So we've been active in outreach and extension. As we get more results, we intend to hit more of these events and venues in the future. So with that, I will open things up for questions. Before I do that, I just want to acknowledge everybody who's part of this team. You can see them scrolling on the right-hand side. There's many people involved. We have a great collaborative team. So thanks to everybody here, and thanks to y'all for your attention this afternoon. I'm going to try to answer some questions now.
Great, thank you so much for a great presentation, Jay. We've been taking a lot of questions in the chat box, and anybody that has any more they'd like to type in, please go ahead and do that. I'll just let you know that if people need to sign off before we get to your question, we will follow up with you later on after we download the questions, and we'll send them on to Jay to answer. So I'd like to start with the first question. Actually received a few questions from Rick Graham, and it seems he may not be able to use his microphone, but we'll give it a shot. Let's see here. Let's see, Rick. I'll give you a second, Rick, to see if you're able to unmute.
Okay, is that working?
Yeah, we can hear you.
Oh, that's good. Well, I've been following this quite a while with my involvements with the Isaac Walton League and with the Lake Erie Foundation. But what is really the biggest factor for the phosphorus running into Lake Erie Western Basin watersheds? The excessive runoff amounts, or is it the soil health issues related to the ability for the soils to hold moisture and retain nutrients? That's my first question.
I would say that there's probably not one biggest factor. I think what you mentioned there, Rick, are two important factors governing this. So if we can identify these fields and identify ways to reduce phosphorus coming off of them, that's important. But I think soil health is equally as important. Soil health is something it's a win-win, right? So if you can have soil health and hold water back, you're also probably going to improve your yield. So that's something that's really attractive too. So, you know, I don't think we know enough, or even if we did know more, I don't think there's one kind of smoking gun. I think it's a combination of factors that we got to look at to reduce phosphorus going into Lake Erie.
Okay, another question relates to the excessive nutrients. Are they primarily from the result of waste disposal operations from livestock operations, confined feeding, or are they relative to just awkward situations from nutrients being applied for crop rotation for different crops?
Yeah, that's a great question. From the sites that we've seen, the majority of them, the cause of that elevated phosphorus is due to past manure application. Whether this is a CAFO or whether this was a small dairy, you know, 30 years ago, all those options are possible, and I've seen all those options. So these legacy phosphorus fields, they have a real long-lasting ability. Some of the sites we looked at, just by talking to people in the area, they will say it's been 30 to 40 years since there was a livestock operation there, but yet we see really high concentration. So the vast majority of them are due to historic manure application. Now there are a couple sites that we've looked at that are due to sludge application or due to over application of inorganic nutrients as well.
Okay, and another part of the question relates to, it's my understanding in talking with a lot of different soil and water conservation people and some NRCS people, that actually the exact locations of the biggest problemed areas are fully known and identified. And it seems to me that we should be really looking to focus more strenuously on those areas. It just seems to make sense.
That intuitively, I agree that does seem to make sense. I think that, you know, we've done some analyses of CAFOs. We did some collaborative work with ODA a couple years ago where we looked at their application rate, phosphorus application rate on the fields they controlled, and all the CAFOs were doing what they should do from what we could tell. Now there are some opportunities for them to deliver their nutrients to other folks, and then they can't be traced. But the data that ODA has from large CAFOs that are using their manure on their own fields are doing what they should do. There's a lack of information about what happens when they transfer that manure off site. So those are just some things that we've learned. None of the sites that we're looking at are large dairies right now. A lot of the sites we're looking at are row crop operations that don't have livestock, but because in the past there was livestock on these areas, there's high soil test phosphorus concentration. So the key for us is finding out, you know, these fields are out there, but what we ideally want to do is use that high soil test phosphorus to have productive crops, but limit how much comes off the field. So that's the real key here. Now the other thing that's not part of our project is how you manage the new manure that's being put on fields, right? And I think that's more your question.
Yeah, it is. With these high phosphorus fields and that, is surface runoff or tile runoff the biggest problem, or is it not separable? And that's my last question. Okay.
Thanks for your questions, Rick. I'm glad you got your mic on. That's a great question, Rick, that we don't know the answer to yet. Kevin King's done a lot of edge of field monitoring from fields more in the agronomic range of soil test phosphorus. It varies widely, but roughly it's, you know, half and half, I'd say, surface and tile. We haven't gathered enough information yet from our sites to tell you if that roughly plays true on elevated phosphorus fields, or if it's more surface or more tile. So I don't know the answer to that question yet, but I hope by the end of the project, or maybe in a year or two, I could have a better answer for you.
I can remember from back in the early 70s when I was at Ohio State in Glenn Schwab's ag engineering, and the discussions that we had when we were at Coshocton Research Center discussing the no-till operations and how effective they were from the '69 flooding. It was amazing to see what the discrimination was on the runoff between what was surface runoff and what was tile runoff. Thank you very much.
Thank you, Rick. Appreciate it.
Thanks, Rick. Next, we had a few questions from Stephen Applebaum. Stephen, I'm going to unmute you on my end. You'll also have to unmute yourself to ask your questions.
Let's see.
Yep, we can hear you.
Well, great. Thank you for the seminar. I had 3 questions. Wondering what the soil sampling depth was that you were using for your infield phosphorus measurements. And then the second question is, do you have any reference to historic phosphorus discharge levels from that might be associated with reference natural areas in the same areas where you've done your field work and agronomic systems? And then the third question is there a filtered P discharge risk if the filters go anaerobic during the winter? And are you sampling year round, so you pick up a first flush in the spring to pick up any discharge that might have higher levels of spring phosphorus?
Okay, I think I might have got 4 questions there, and I'm gonna try to answer them in reverse order because that's how I'm remembering the best right now. We are sampling year round, so we will pick up you know, trends that happen in the spring, fall, summer, or whenever they happen, we should be able to see them. We do have heaters in our monitoring equipment, so we're sampling year round. You ask about anaerobic. We do have that concern. That was especially a concern of ours where we're using the iron filings mixed with the
right. Yep.
Mixed with the sand. We have thought about that. We don't think it'll be a problem, but we are concerned about it. So we're going to have some redox monitors in some of those systems to see the water that comes off of those of the tiles has pretty good oxygen concentration in it. And most of those tiles flow pretty regularly. So there should be pretty good flow and turnover within those structures. But we are concerned about it. We are going to monitor it. That's about the best I can tell you there.
And then the last question was soil sampling depth for your field sampling.
Yeah, I'm blanking right now, but we're using the standard, I think, is it a 6-inch depth?
Okay.
And then we are actually we're working with Chad Penn just in the near future here, and we are going to take some deeper samples as well in some of the fields to try to get try to find out what's happening not just in that top 6 inches, but what's happening below that as well.
Yeah, that my question was focused on is the soil column not just the upper 15 centimeters or whatever the source of the phosphorus, or is it actually mobilized under anaerobic conditions from surface strata down into lower stratum and then enters the tile system? Now, I guess there was a third question. That was the historic reference. What were the historic P discharges from the soil types that you're working with compared to the current manure, nutrified levels? Any reference to the historic reference areas?
I don't have a question. I don't have an answer to that question.
Okay.
I can go back to your soil depth question, because we have looked into a couple of the sites. We have looked into depth more. So where we're likely going to construct a wetland, we know that we couldn't have really high soil test phosphorus in the bottom of that wetland. So we needed to find out how deep we had to remove soil. So we didn't have that.
Okay.
That in there, and we found out that most of it was in that top 6 inches or so. So we thought that if we remove the top 6 inches of soil, we could remove most of the elevated P and get down to a safe level of soil that wouldn't leach phosphorus back into that wetland when it was anaerobic after it became flooded. So at least for that field, the high concentrations were limited to that top 6 inches.
And that's based on not sampling dynamic phosphorus mobility. That's just based on a static sample of phosphorus at different levels.
That's right.
Okay.
Yep.
Okay. Okay. Well, thank you very much again for the seminar and your answers. Thanks so much.
Thanks for your questions.
You're welcome.
All right. Thanks, Stephen. And we'll take just a couple more questions. And I apologize again to anyone we didn't get to. We will download those questions and see if we can get some answers to you. But the last couple of questions we'll take are from John Bratton. So John, I will unmute you. And as you're unmuting yourself, I'll also let everybody know that we will be posting the video recording of the seminar on the Sigler website, and I'll put that link into the question box for people to see. So go ahead, John.
Okay, thanks, Mary.
Oops. Sorry about that, John. I meant to mute myself and I muted you. Just give me 1 second to scroll back down to your name. I apologize. Okay, you can speak now. I'm sorry about that.
Excellent. I'm glad it wasn't me. Some of the questions anticipated mine about manure hotspots. The idea of kind of, I don't know what you call it, paleo manure is interesting, and figuring out historical applications where there might not be an operation anymore. The other question I had is related to plugging and fouling of the filters. I assume there's at least two elements to that. One might be sediment within the tile drains themselves, and the other be processes happening, either precipitation or microbial buildup within the filter itself. Could you comment on design considerations that were incorporated to address those? It sounds like they haven't plugged yet, but is that luck or that was intentional design?
It's not either one. It's the fact that we just started adding water to them, so they haven't had time to clog yet. No, but we're very concerned about clogging. Working with Chad, we know that that's a big limitation of these phosphorus filters. And as you anticipated, John, that can happen in at least two ways. One of those is if you have a lot of sediments that get into that phosphorus filter. So for that reason, a lot of these phosphorus filters are used with tile only water. So If you get drainage tile water, it just doesn't have the sediments in it and soil and things you get from surface runoff. The other avenue for clogging is precipitation, like you said, and we've seen that happen in some of these in the past. The primary way that we are trying to combat that is by having more porous media. So the alcan has more porosity in it. And with the metal shavings, those have been proven to work really well in the lab and pretty large scale lab tests. But a lot of those have been using sand to hold those metal shavings within the structure. And getting away from sand, we're actually using larger pea gravel now, so we have more porosity in there. The other critical threshold for these is actually the collection pipe at the bottom of the structure. And so some of those in the past have had fairly small holes, so pretty easy to get clogged. So right now we're using well screenings or well screens, the same things you would use on a drinking water well to screen the water that's coming into there. And we think that's going to help a lot because they have bigger holes to allow the water through the pipe and allow some other solids and things like that. So kind of just physically addressing those concerns right now is where we're at. But we do think with talking to Chad and thinking about it a little bit that those should help us combat clogging.
And you briefly touched on regeneration. Would that be in situ, or that would be removal of media and regenerate and put it back?
It definitely could happen either way. What we want to try to do is in situ. So use some acid that we pump back through the system that removes the phosphorus and lets us recharge the same media and use it again. This is a hope, I guess. I don't think this has been demonstrated yet, but Chad thinks it'll work, and we might be up for trying it. That would be something that would probably happen 4 or 5 years from now, I guess. The way we've designed all these is that we gave them the design life of at least 4 or 5 years. If we do find that they're becoming saturated sooner than that, we may have to try recharging beforehand. So that's another thing that we hope to learn from this project and some of the other installations of phosphorus filters that are going in around the Western Lake Erie Basin.
All right, that's it for me. You got your hands full. Good work.
Thanks, John.
All right, thank you, John. And thank you so much to everyone who attended today. And of course, thank you so much to Dr. Jay Martin for a wonderful presentation, answering as many questions as we could get to. And again, we'll try to get questions out to everybody that we were not able to address. So thank you again, everyone, and hope to see you soon at a future Great Lakes Seminar Series talk. Have a wonderful afternoon. And don't forget to vote. Bye.
Bye, Mary.
Bye.